Hello friends, welcome to the sixth lecture of function. In this lecture of calculus, function part 6, we will be studying about different types of mapping and we will also talk about inverse function. Let me tell you about different types of mapping. We know that function is a relation between two sets. One set consists of all valid input values and other set contains the output values of function. The set which contains the input value is known as domain and the set which contains the output values is known as codomain. And the set of collection of all output values is known as range. And I have already told in my previous lecture. So, function is a rule for assigning unique values from codomain to the elements present in the domain. Now we can assign the elements from codomain to elements in domain in a one-to-one fashion or in many-to-one fashion. So what is one-to-one function? By the name, it's clear that exactly one element from codomain is assigned to a unique element present in domain. Let f of x is a function defined within a domain D and is one-to-one. That means for each output value of function which is f of x that belongs to codomain, there is only one input value, say x, is assigned which is present in the domain of function. Or in other words, we can say, suppose x1 and x2 are the input values present in the domain of function f of x, and if x1 not equal to x2, then the output of the function f of x1 and f of x2 are not equal, then we can say that the function is one-to-one. So how we can test whether the function is one-to-one? We can test whether function is one-to-one by a horizontal line test. Let me show you an animation for identifying one-to-one function. Here I have drawn the graph of a function y equal to f of x, which is shown by red color line. Now I have drawn a horizontal line and which intersect the graph at only one point. So from the graph we can see the coordinate of the intersecting point has only one y value for only one value of x. So we can tell the function is one-to-one. Now let us see a many-to-one function, because the function which is not one-to-one is known as many-to-one function. So I have drawn again another graph of a function y equal to f of x, but now we can see that the horizontal line intersect this graph of the function at three different points. From the graph we can see that the y coordinate of three intersecting points is same for different value of x. So this blue color graph is not one-to-one as per the definition of one-to-one function. So let us take an example of a known function. So I have drawn here a known function which is y equal to x square, which is a parabola, and we can see that the parabolic function is not one to one because it intersects the horizontal line at two different points. Now let us look into the square root function. So what we can see? We can see that the horizontal line intersects the square root function at only one point. That means it has only one output value which is assigned with only one input value. So y equal to square root of x is one to one function. With this example, I will show you how to check whether function is one to one. So just in the previous slide, I have told that choose any two values, say x1 and x2, within the domain of the function, that is D. And if the value of the function at x1 and x2, that is f of x1 and f of x2, are not equal, whenever x1 and x2 are not equal, then function is said to be one to one. But we can't use the definition of one to one function directly to show a function whether it is one to one or not. Then instead of using definition directly, we will say that even if x1 is not equal to x2 in the domain of the function, and we get f of x1 and f of x2 are equal unless only when x1 equal to x2, then we can say that our function is not one to one. So first we will evaluate f of x1 equal to f of x2 in this example. So here in this example, f of x is equal to x square plus 4x plus 7 by x square plus x plus 1, and we choose x1 and x2 belongs to domain of f, and we will evaluate f of x1 equal to f of x2, that is x1 square plus 4x1 plus 7 by x1 square plus x1 plus 1 equal to x2 square plus 4x2 plus 7 by x2 square plus x2 plus 1. Then after solving, we get an equation whose left hand side consists of product of two factors. One factor consists of x1 minus x2 and the other twice x1 plus twice x2 plus x1 x2 plus 1, and both of them are equal to 0. So the solution will be either one of them is 0. So while solving x1 minus x2 equal to 0, we will obviously get x1 equal to x2, and we know if x1 equal to x2, then obviously f of x1 is equal to f of x2. But our concern is not x1 equal to x2. We will see whether f of x1 becomes equal to f of x2 even if x1 is not equal to x2. So we will try to solve a second factor in the above equation, which is twice x1 plus twice x2 plus x1 x2 plus 1 equal to 0, and we can see that if we choose x1 equal to 0, we get the value of x2 is minus half. So we get f of x1 equal to f of x2 when x1 is 0 and x2 is minus half. That means the function's value are same for two different input values. So the function is not 1 to 1. Another type of mapping is onto function. So let us look into it. Let f is a function from a to b, and if each element in the codomain b has at least one value assigned in the domain a, we can say the function is onto. And what is into function? If there exists at least one element in the codomain b which is not assigned to any element in the domain a, we can say the function is into function. So let us look into the animation so we can understand better what is onto function and into function. Consider two set a and b, where set a consists of some natural numbers 1, 2, 3, 4, 5, and set b consists of some natural number 1, 4, 9, 16 and 25. So here can you tell based on what rule I have assigned this number from a to b? Here the rule is square. You can see all the elements in b are the square of the elements present in a. So here domain is a set A which consists of element 1, 2, 3, 4, 5, and codomain is a set B which consists of number 1, 4, 9, 16 and 25, and here range is also set 1, 4, 9, 16, 25, which is equal to the codomain. So the functions where range is equal to the codomain, or we can say range is a proper subset of codomain, then the function is onto function. Now let us look into the into function. Here look into the set of the B which consists of element 1, 2, 3, 4, 9, 16 and 25. So from the figure we can see all the elements of the B are mapped except 2 and 3. So here domain is set A which consists of element 1, 2, 3, 4 and 5, and now the codomain is set B which consists of 1, 2, 3, 4, 9, 16 and 25. And what about range? Remember, range only consists of the output value of the function. Here the output value of the function is 1, 4, 9, 16 and 25. Now we can see here range is a subset of codomain but not a proper subset. That means the elements of range does not include all the elements present in codomain. So this type of function is known as into function. Now how to check whether function is onto or into? So we will solve f of x equal to y for x and find x as a function of y, say g of y. Now if g of y is defined for each y belongs to codomain and g of y belongs to domain of f for all y belongs to codomain, then the function is onto. A function which is both 1 to 1 and onto is known as bijective function. So let us take one example so that we can understand better how to check whether function is onto or into. Here let f is a function from closed interval 0 to 1 to real number. That means here the domain is in a closed interval 0 to 1 and the codomain is a set of real numbers, and I choose the function f of x equal to x square. So how to check? We will choose a variable y which will be equal to y equal to x square. Then we will find x as a function of y. So we can write x equal to square root of y. Remember, here I have chosen y equal to x square. Now when we will write x equal to square root of y, it will not only be a square root of y, it should be plus minus square root of y. But here, as I have already defined that my domain is from 0 to 1, so here the value of x is positive. So we will choose only x equal to positive square root of y. Now we have to find the range of function x equal to g of y, and we will choose the value of y from the codomain of f of x, which is all real numbers. Now if the range of g of y is equal to the domain of f, then the function is onto. Now we know that the function x equal to g of y has a range of all positive real numbers including 0. But here in this example, the domain of the function f of x equal to x square is close interval 0 to 1. So clearly the range of g of y is not equal to the domain of the function f. So the function f of x equal to x square is not onto, it is an into function. As we have already studied one-to-one function, since each output of a one-to-one function comes from just one input, the effect of the function can be inverted to send an output back to the input from which it came. Consider that f is a one-to-one function on a domain D with range R, where R is a set of real numbers. The inverse function f to the power minus 1, which is read as f inverse, is defined by f inverse of b equal to a if f of a equal to b. The domain of f inverse is R, which is the range of the original function f, and the range of f inverse is D, which is the domain of the original function f. Note the symbol f inverse does not mean 1 by f of x. So let us take an example for better understanding of f inverse. Given a one-to-one function y equal to f of x by a table of values, we can see the table in the right side of the slide, where I have given a table for f of x which consists x values as 1, 2 and 3, and the function output value f of x as 3, 5.4 and 9. So what is the domain of the function f of x? The domain of the function f of x is 1, 2 and 3. And what about the range of the function f of x, which will be 3, 5.4 and 9. And just below the table for f of x, I have shown a table for f inverse of y. A table for the values of x equal to f inverse of y can then be obtained by simply interchanging the column or rows of the table for f. As I have just told in the previous slide, that the domain of f inverse is the range of the original function f of x. So here the domain is the y values, which is the same as the range of the function f of x, which will be 3, 5.4 and 9, and the range of f inverse will be the same as the domain of the function f of x, which will be 1, 2 and 3. Another way of interpreting function is to think function as a machine. So here I have considered two machine, one is f and another is f inverse, which is shown in green color block. And if we feed x as an input value to the first machine, which is f, it will give an output value f of x. And again feeding f of x as input to the second machine, which is f inverse, then what we will get in the output, we will get f inverse f of x, like a composite function, and the value will be equal to x. So actually what f inverse do, f inverse will simply revert the action of the first machine f. Now let us look into the graph of the inverse function. That means how to draw the graph of the inverse function. The graph of a function and its inverse are closely related. So first let us draw a graph of a function, which is y equal to f of x, shown by purple color line in the figure. This blue color line shows the domain of f, and this red color line represents the range of the function f. Now to read the value of a function from its graph, we start at a point x and on the x-axis, which goes vertically to the graph, and then move horizontally, as I have shown by a yellow color line, to the y-axis to read the value of y. The inverse function can be read from the graph by reversing this process. So start with the point y on the axis, go horizontally to the graph of y equal to f of x, and then move vertically to the x-axis, as shown by a little animation I have played here, to read the value of x equal to f inverse of y. So here the graph is x equal to f inverse y. So now the blue color line gives you the range of the f inverse. As I have already told, that the domain of the original function will become the range of the f inverse, and the range of the original function will become the domain of the f inverse. So here the domain of f inverse is shown by the red color line, which is the range of the original function f. So in the previous slide we have seen that how to read the values of f inverse from the graph, and also in the previous slide we have seen that the input values of f inverse is lie along the y-axis, and the output value of f inverse is lying along the x-axis. Here I want to set up the graph of the f inverse so that its input value lie along the x-axis, which is normally done for the function, rather than on the y-axis. So here y equal to f of x is the original graph, which is shown by the purple color line. Now to set the graph of the f inverse so that its input value lie along the x-axis, we will achieve this by interchanging the x and y axis by reflecting across the 45-degree line y equal to x, And after performing reflection of the graph y equal to f of x, we have a new graph that represents f inverse and the domain of f inverse will now lie along the x-axis and the range of f inverse will be along the y-axis, which is normally done usually for any function. So what is now we can see the graph of the f inverse in another graph. So here the value of f inverse can now be read from the graph in the usual way by starting with the point x on the x-axis, going vertically to the graph and then horizontally to the y-axis to get the value of f inverse of x. Now, what are the steps for finding inverse function? The process of passing from f to f inverse can be summarized as two-step procedure. Solve the equation y equal to f of x for x. This gives a formula x equal to f inverse of y, where x is expressed as a function of y. The second step, interchange x and y variable, obtaining a formula y equal to f inverse x, where f is expressed in the conventional format with x as the independent variable and y is the dependent variable. So let us take an example for better understanding of inverse function. So find the inverse of y equal to 0.5x plus 1 expressed as a function of x. So first step, we have to solve for x in terms of y. So here y equal to 0.5x plus 1, and then in the next step we can write twice y equal to x plus 2, and then we can write x equal to 2y minus 2. So now we have solved for x in terms of y. So in the next step we have to interchange x and y to express in a conventional manner. The inverse of the function f of x 0.5x plus 1 is the function f inverse x, we can write twice x minus 2. Here you can see I will just interchange the value of x and y from the equation x equal to 2y minus 2. And we can also check whether the function twice x minus 2 is the inverse of 0.5x plus 1. How to check? As we have discussed in my previous slide, that when we use the composite function f inverse f of x, we will get the answer always x, which is the input value to the original function f of x. So here if we do the composition of a function f inverse f of x, that is twice into 0.5x plus 1 within the first bracket minus 2, and then which is equal to x plus 2 minus 2 and ultimately equal to x. Or say in other words, we can write f of f inverse of x, which will also give you the same answer x. So in this way we can check whether the function is inverse of the original function or not. Now take another function y equal to x square, and where domain is restricted, which is x greater than or equal to 0, and we have to express the inverse as a function of x. So to find the inverse, we first solve for x in terms of y, that is y equal to x square, which implies square root of y equal to square root of x square, which is equal to mod of x and mod of x is equal to x here because x is greater than or equal to 0. We then interchange the value of x and y to obtain f inverse as a function of x, which will be y equal to square root of x. Now let us see the animation for better understanding. Now we know how y equal to x square graph looks like. It is a parabola. Now to find the inverse of the function, as I have already told that the function should be one-to-one function. Now how to check one-to-one function? We have to draw a horizontal line and see whether this horizontal line intersect at only one point or more than one point at a function. So here from the figure we can see the horizontal line intersect the function at two different points. Now if the horizontal line is at a height of 1 unit from the x-axis, we can say when we move over the horizontal line, all the point has y coordinate which is equal to 1. And we have seen the function has a output value 1 when its input is either 1 or minus 1. So it is not one-to-one because here for two different input we are getting the same output. Now if I put the restriction on a domain, that is x greater than or equal to 0, now we can see from the graph that there is only one point corresponding to the output value 1 in the x-axis. Now how to draw the graph of the f inverse? Now we have to reflect this graph along the 45-degree line y equal to x-axis, so that we can get the graph of f inverse, which is the graph of square root of x. So here both algebraically and both graphically we have seen how to find the inverse of a function. So in the next part of the lecture we will talk about trigonometric function and how to find the inverse of trigonometric function. So thanks for watching. Stay tuned and stay